All right, this will be the video for differential equations, section 7.3, day, actually, this is labeled wrong, this is day 3. So let me change that. This is day 3. And this is going to be the last of the Laplace transform properties that we talk about. This is shifting on the t-axis. We talked about shifting on the s-axis in day 1. Day 2, we talked about how the unit step function works. And now we're going to talk about how we can use that unit step function to shift on the t-axis and the Laplace transform properties of that. All right. So that's actually the 3rd day. All right, so earlier we described the result of taking a Laplace transform of a function in the t-domain. We said that if you multiply a function in the t-domain by e to the at, then it's the Laplace transform of that f, capital F, but shifted a in the s-domain, right? So Laplace transform, if you have the shift in the s-domain, it's equivalent to multiplying by e to the at in the t-domain. So maybe you might be wondering, well, what happens if I shift in the t-domain, or is there anything that is equivalent to multiplying by e to the as in the s-domain? And the answer is yes, that works as well. It turns out that if you take a Laplace transform function f of s that's not shifted, but you multiply it by e to the negative as, that's equivalent to a shift in the t-domain, but also multiplied by a unit step function with that same shift. So it's a complete shift and turn on of the f function of the value a. Okay. One thing to keep in mind here that when you look at these is, right, this is minus a here, but the exponential is positive when we're shifting when the exponential is multiplied in the t. When it's multiplied in the s, it's negative, right? But other than that, right, multiplying by e to the a negative as in the s domain is equivalent to shifting in the time domain, but also multiplying by unit step function. That turns out to be very useful because it's the property that's going to allow us to take the Laplace transform of right-hand side driving functions, which are abruptly turned on and off or shifted in time, which is very helpful. And these, there's a couple of additional ones that are useful to know. Sometimes we want to know just what's the Laplace transform of just a unit step function not being multiplied by another function. So just the unit step function itself. And that just turns out to be e to the negative as over s, where a is the constant of shifting here. And then this happens sometimes too, right? If you look at the way this works, you have to have some function which is shifted the same amount as the unit step function in order for this to work in this form. But a lot of times we'll have a function that's either unshifted or shifted to a different amount, and the unit step function is not the same. Like maybe you'll have a function of t, but then a unit step function that turns it on at some other time, but the function isn't shifted. So this property turns out to also be useful. And that is that the Laplace transform of a function g of t and then multiplied by unit step function that shifts over a is equal to e to the negative as times the Laplace transform of the g of t plus a. So you shift in the opposite direction and still multiply by an e to the negative as. Okay. Easiest to see all these things in context by looking at examples. So we'll look at a number of increasing complexity examples here. The first one is, let's say we just want to find the Laplace transform of e to the 2 minus t times the unit step function t minus 2. So first I might write that as e to the, let's see, maybe I could write that as negative t minus 2, so that I can see that, in fact, this shift and this shift are the same. So there's a property that says that if this is shifting, so if I have a is 2 here, because this is shifted over, then that means that what my function is really, my f of t here, is really just e to the negative t, but with a shift, right? So the Laplace transform of e to the negative t would be 1 over s minus negative 1, or 1 over s plus 1, right? But I have to multiply that by the exponential. So In this case, this isn't the exponential multiplication. This is the f of t. And that means that the Laplace transform of all of this is just going to be this 1 over s plus 1, right? But times an e to the negative 2t, or negative 2s, sorry, negative 2s. So, right, if you have a shifted in time multiplied by a unit function of that same shift, the Laplace transform of that is the Laplace transform of the function 1 over s plus 1, but multiplied by e to the negative 2s. Shifting in time multiplied by an exponential in s. And in this case, the exponential is negative. It's negative for the s case. It's positive for the time case, the t case. Okay, let's look at another example. Let's take the Laplace transform of a function that's defined piecewise. So first I'm going to take this function and graph it and then express it using step functions. So it's 1 from 0 to 4, and then it switches to 0 between 4 and 5, and then it goes back up to 1 at 5 and stays on there forever. Okay, so the way I could write that with unit step functions is say start with a unit step function that makes it 1 starting at t equals 0, but then subtract off a unit step function starting at 4, and then add back in a unit step function starting at 5. So here's a way to express in a single expression with unit step functions this piecewise function, okay, using the techniques we did yesterday. And that means that I'm going to take the Laplace transform of that. So what's the Laplace transform of a unit step function minus a unit step function shifted 4 plus a unit step function shifted 5? Okay, so the Laplace transform of a unit step function, if we look at that little formula there, is the Laplace transform of a unit step function, t minus a, is e to the negative as over s, right? Just double checking. E to the negative as over s. So this first one has a shift of 0. So this one's going to be e to the negative 0s over s. This one's going to be e to the negative 4s over s. And this one's going to be e to the negative 5s over s. And so probably we would just write this as 1 over s minus e to the negative 4s over s plus e to the negative 5s over s. So this would be the Laplace transform of this piecewise function. So that's where the real beauty is. Now that we have the unit step function, we can use these properties to take Laplace transforms of very complicated functions where things are switching on and off or have abrupt changes in behavior. Okay, here's another one. We're taking the Laplace transform of sine of t, u of t minus 2 pi. So what I see here is no shift here, but here there's a shift. So that's where we're going to take advantage of this property that the Laplace transform of a function g of t, unit step function of t minus a, is equal to e to the negative as times the Laplace transform of the g function shifted plus a in the opposite direction. Okay, so what we'll have here is the g of t function here is sine. So what we could say is that this is equivalent to saying we're going to have this over here. The shift a appears to be 2 pi. So this is going to be equal to e to the minus 2 pi s, right? There's this part. But then we have to take the Laplace transform of this same function sine, except shifted plus 2 pi. So t plus 2 pi. So I'll have to take the Laplace transform of this sine. But luckily, the sine function is periodic. So whatever t is, if you go 2 pi, it's exactly the same. So this is equivalent to e to the negative 2 pi s times the Laplace transform of just sine of t. And sine of t is on our table, right? We know that that one is 1 over s squared plus 1, if this is a 1. So this is the answer. Okay, so that's how we deal with it if there's no shift in the function, but there's a shift in the unit step function. So far, these have all been Laplace transforms. Let's try an inverse Laplace example. So let's say we have this. Maybe I could write this first of all as inverse Laplace of, we have this e to the minus pi over 2s, and then we have s over s squared plus 4. Just write a little nicer so I can see this part separate. Because whenever I see something like that, it means that this right here is my a. My shift amount is negative pi over 2, right? And then this right here transforms to cosine, right? Cosine of 2 t, right? So I'm going to have a shifted version of cosine, right? But also multiplied by a unit step function. So this is going to be equal to the cosine of 2, but I'm going to take the shifted version now. So this t is going to be replaced with t minus pi over 2. And then that whole thing is multiplied by a unit step function with the same shift. So it's this function not only shifted pi over 2, but also turned on at t minus pi over 2, or turned on at t equals pi over 2. Okay, so this would be the result of that inverse inverse Laplace transform. Okay, and then I want to show you two examples here of solving differential equations in this manner. So these will be a little bit longer. The real beauty of all this is to be able to deal with right-hand sides, differential equations with right-hand sides that are involving abrupt changes. So let's say we have this. We have this differential equation y prime plus y equals f of t, where f of t is abruptly changing in time. It's 1 from 0 to 1, and then it switches to negative 1 here. And continues, and then we have an initial condition. So first of all, I could rewrite this f of t as start with the unit step function at 0, and then subtract 2 unit step functions. So not only do you cancel it, but you add a negative version in. So subtract 2 unit step functions starting at t minus 1. And so let me rewrite this as y prime plus y equals unit step function minus 2 unit step functions t minus 1. Okay, so now we have something where we can take the Laplace transform of everything. Let's take the Laplace transform. I'll use black. To do that, we've got the derivative, which is sys minus y0 plus the y, which will be ys. And then the Laplace transform of unit step function, this is with shift of 0, so that would be e to the 0s over s minus 2 times Laplace transform of unit step function shifted 1, so that's going to be e to the negative 1s over s, right? If I kind of factor out the y's's here, I have s plus 1 ys, and then actually this is y of 0, and y of 0 they said was 0, so that is 0 here. And then let me write this just as 1 over s minus 2 e to the negative s over s, okay? And then actually, let me write it maybe as a little bit differently. Let me write this as 2e to the negative s and then times 1 over s, okay? Then you would divide through everything by this s plus 1, so you would get ys equals 1 over s times s plus 1 minus 2 times e to the negative s 1 over s times s plus 1. And then you could use a partial fraction expansion, maybe online, to get that 1 over s plus 1 is equal to 1 over s minus 1 over s plus 1. So both of those can expand using partial fractions to give me ys is 1 over s minus 1 over s plus 1 minus 2e to the negative s 1 over s minus 2e to the negative s 1 over s plus 1. And now we're ready to do the inverse Laplace transform. So if I take the inverse Laplace transform, this will become y of t. 1 over s is just 1. 1 over s plus 1, so minus, this is going to be e to the negative t. Then I've got minus 2. This is a shifted by 1 version of 1 over s, right? In fact, actually, if I recombine this as e to the negative s over s, this is just the unit step function at shifted t minus 1. And then this one is a shifted version of 1 over s plus 1, right? So 1 over s plus 1, this is the inverse Laplace of this is going to be e to the negative t, except shifted in time 1. So we've got minus 2. We've got e to the negative t, but shifted in time, so t minus 1, and then also times the unit step function. So this right here is the result of that. Okay, and if you were to graph that, I have that in the notes here. Let me take this and copy it to show you what the graph looks like of that. Right, it starts out with these terms that don't apply. These terms don't apply until 1, so they don't happen until here. But up to that point, right, e to the negative 0 is 1, so 1 minus 1 is 0. And then this term drops off, so we subtract less and less, and this has a negative exponential decay curve, so ramps up. And then at time t equals 1, there's a sudden change in behavior because of this this large negative input, this impulse that drops this down quickly. And so there's a quick change in behavior. The output system to respond to that very large change in negative direction of the driving function. And then that effect of that settles out over time as well. All right, so an interesting result. Let's take a look at one other example. Here's a second order differential equation with a shifted cosine turning on, unshifted cosine, but turning on at t equals pi. So first we could start with derivative, so the Laplace transform. So the Laplace transform is going to be s squared y s for the second derivative minus s times y0 minus y prime 0, right? Plus 4 times just y, so ys equals this. Now this right-hand side there's a unit step function and this cosine. So the function is cosine, the shift is pi, right? So this is going to be the equivalent of e to the negative pi s times the Laplace transform of the cosine, but shifted in the other direction, pi. So plus pi. Okay, but the thing about cosine is if you're at some position t here, and you go pi, t plus pi over here, t plus pi, the cosine is always the negative of whatever it would be on the other side of the circle. So this is equivalent to taking e to the negative pi s Laplace transform of negative of just cosine of t. And the reason I want that is that I have this in my table, right? So now I could factor this negative out, e to the negative pi s Laplace transform of just cosine of t, which I know is, let's see, s over s squared plus 1. All right, so that's what's equal to this. Let me go ahead and factor out the y term. So we have an s squared plus 4ys. And then let's see, if we plug things in here, the y zeros are 0 and the y prime is 1. So it looks like we do have no s term here, but we have a minus 1. So I'm going to have to move that to the other side as well. So I'm going to have ys equals 1 minus e to the negative pi s over s squared plus 1. And then if I divide through by this, I'm going to get ys equals 1 over s squared plus 4 minus e to the negative pi s. And then I have s over, and I'm going to have an s squared plus 4 and then the s squared plus 1 there as well. Okay, so we're going to need to have partial fraction expansion for this. Let me go ahead and switch colors here. The partial fraction expansion for s over s squared plus 4 and s squared plus 1 turns out to be negative 1/3 s over s squared plus 4, and then plus 1/3 s over s squared plus 1. All right, so swapping that out, we're going to have, get some more room down here. We've got ys equals 1 over s squared plus 4 minus e to the minus pi s, and then this first term, which I'm going to now make this plus 1/3, and then s over s squared plus 4. And then I've got minus 1/3, so minus 1/3 e to the pi s, and then s over s squared plus 1. All right, so now we're ready to do the inverse Laplace. That will make this left-hand side y of t. This first one, if we fix up constants here, if I multiply this by 2 and divide by 2, this is the form that I need to get sine. So I have 1/2, let me switch to black here. I have 1/2, and this is sine of 2t, right? And then this one here is in the form for cosine of 2t, right? But there's a shift here of t minus pi. So we're going to have plus 1/3, and then this is going to be cosine of 2t, so 2 times t minus pi, but then that doesn't turn on until t minus pi, right? The shift also turns on at the same time. And then the same thing over here, but it's minus 1/3. And this one is the same thing, but cosine, but this time with the argument frequency of 1. So it's going to be a cosine of 1t, but t minus pi, and then unit function t minus pi, because that's also shifted pi. So here is the solution curve. Okay, and if you were to graph that, I'm going to take that and just show you, because I graphed that with GeoGebra online. That looks like this. Okay, let me get rid of this. Yeah, so right, these other two terms, they don't turn on until pi, so not until 3.14 right here, right? Before that, it's just a 1/2 sine of 2t, a nice sine wave, but right through its curve, right there, it abruptly changes, and now there's a mixture of cosine of that same 2t and a cosine of half of that, which is why this gets more complicated looking, because it's a more complicated sinusoid. Okay, so if we do this where we're applying a cosine wave, but not until later, right? What's happening is the natural function wants to resonate at a sine of 2t. So this comes from just driving it at all. And then when the driving functions switch on at 2 pi, this starts to shift, and then there's a combination of what's going on in the natural resonance along with the driving function. All right. So you can see how this is the basis of vibrational analysis, which is really complicated and very important for mechanical systems design. All right, that's the last example for this. You should be able to do problems at this point from the homework, and then come to tutoring if you have any questions.